This is Eugene Augustine once again, and this is the second part of my industrial training for fresh electrical engineers and also for the final year students of electrical engineering. Last time I had asked you 10 questions and you were supposed to send me the answers by email. I have received some of your answers, thank you. Therefore, I dedicate this session especially for those who have taken the trouble of sending me the answers. But before I start, I would like to make a special mention of a girl from the 2019 batch of Goa Engineering College. The answers were really wonderful. I corrected her question paper and she has scored 60% marks. She is presently working in a reputed company in Rajasthan, and within a span of less than 1 year she has gained tremendous practical knowledge. Well done. So shall we start off? So I have decided now to answer 4 of your questions. Question number 1, which is very important, then question number 3, 6 and 9. So out of the 10 questions, 4 questions I am going to answer today, and in my next session I will take up the other 6 questions, which are much smaller ones. Okay? So if you remember what was my first question last time, it is about a 3-phase lighting circuit. In a 3-phase lighting circuit, either in an industry or in a residence, if suddenly the neutral wire goes off or gets disconnected, what would happen to the lights, fans, AC, etc. that were on? I had given a choice of 3 answers, and obviously all of you have selected the first answer, that is, when some lights, fans, AC, etc. are on in a 3-phase lighting circuit and suddenly the neutral wire gets disconnected, then all the lights and other equipment that were on will go off, because without the neutral the circuit cannot get completed. This was the answer, the first answer, and all of you chose that particular answer. I am not going to dispute whether this answer is correct or not, but I want to show you a demonstration, a live demonstration, so that you will understand the importance of a neutral in a 3-phase lighting circuit. Okay? So for this purpose, I have made a special test board to demonstrate to you. Okay? And before I show the live demonstration, I'll try to explain to you the circuit diagram of this particular test board, so that you will understand what it is. Now this is the circuit diagram of the test board. The 4 incoming wires from the R phase, the Y phase, the B phase and from the neutral are connected to the 4 terminal connectors, also marked as R, Y, B and neutral. From here, the wires from R, Y and B are connected to 3 switches, S1, S2 and S3. Once these switches are on, the wires are connected to one end of the lamps, L1, L2 and L3. The other end of the lamps are connected to a common point marked as star point and brought to the 5th connector on the terminal connector. Another switch S4, that is the neutral switch, is connected between the neutral terminal and the star point. When S4 is on, the neutral is connected to all the 3 lamps. When S4 is off, the main neutral gets disconnected. The star point is provided so that the voltage across each lamp can be measured between each phase and the star point, even when the neutral is disconnected. During the test, a clamp meter or a tongue tester will be placed in the neutral wire to continuously measure the current drawn by the neutral, and another meter will be placed across each phase and the star point to measure the voltage of each lamp as and when required. Now we will move on to the actual demonstration. For this, I will take you to our workshop, courtesy National Engineers, Goa. Now, can you see the test board? Okay, exactly like it was in the drawing. This is the terminal connector, okay, with the 5 terminals, R, Y, B, the neutral which is black, and then the 5th connector is left open from outside. This is the star point, okay. Now this are connected to our panel here. This is a workshop, electrical workshop here, and courtesy National Engineers, Goa. It is connected to the 3-phase supply, and the board is connected, okay. And now we'll switch on. There are the 3 lamps which are there. Right now I have used lamps of 40 watts, okay, 40 watts 230 volts bulbs, and these are the switches S1, S2, S3 and S4. Now I'll switch on the supply, okay. Now the supply is on and I'm measuring the voltage between phase and neutral, okay. This is first phase, R phase. It is showing 230 volts, okay. The Y phase to neutral is also showing 230 volts, and B phase to neutral is also showing 230 volts, okay. Now this is the supply voltage. All the 3 phases are available with the neutral. Now I will switch on the first lamp, S1, okay. Since the neutral is off, it is not lighting, so I am putting on switch S4. Lamp S1 has switched on, and I have connected an ammeter in the neutral wire. It is showing the current of this particular lamp. It is showing about 0.15 amps, okay. That is almost correct for this 40 watts bulb. Now I am putting off this light S1. I am switching on S2. S2 is also lighting, and again it is showing almost the same current, 0.15 amps. I switch off S2. Now I come to the third one. S3 is on and the neutral also is on, therefore light S3 is working. Now I'll switch on all the 3 lights, S1, S2, S3. All the 3 lights are working, okay. Now see what has happened to the current. The current is showing almost 0. Now the current is almost showing 0. Each bulb was showing 0.15 amps, but when I switched on all the 3 lights, the current in the neutral wire is showing almost 0. Now then why do you need a neutral? Right? I don't know. So I am going to switch off the neutral. Let's see what happens. Surprise. Neutral is switched off, but all the 3 lamps are working. And just check the voltage of each of the lamp between a phase and the star point. First phase with the star point, it is 230 volts. It is showing 230 volts. Second phase with the star point, it is also showing 230 volts. Third phase, the star point, it is showing 230 volts without neutral. All the 3 lamps are working beautifully without neutral, okay. Now we will make a slight change. I will change the bulbs now. I am going to keep one bulb for 40 watts. I am going to put a 60 watt bulb in the second phase, and I am going to use a 200 watts bulb in the third phase, okay. Now we will repeat the test, okay. The power supply is on as before. Now I am going to neutral switch is on. I am switching on the first light. It is lighting brilliantly because neutral is on and drawing almost the same current as before, 0.15 amps, okay. Now I switch off this. I put on the second light. So it's lighting and it is getting 230 volts. Now I go to the third light, 200 watts. This is a 200 watt bulb. This is also getting 230 volts. And now, as before, I am putting on all the 3 lights along with neutral. All the 3 lights are lighting with the full brilliance. Please check the voltage between phase and star point. Our phase to star point, 230 volts, Y phase to start point 230 volts, and B phase to start point 230 volts. Okay, now I just want to put off the neutral. Before that, I'll connect the voltmeter to the first bulb. Okay, connect between R phase and start point. Just connect the meter. Now just watch what will happen when I switch off the neutral. Okay, I will just switch off for 2 seconds. Just watch what is happening. Meantime, I will just take the reading of the voltage. What is happening? Have you noticed what happened? I will do it once again. Just watch. Okay. The bulb L3 almost went off. It was so dim, it was almost off. Whereas the bulb L1 became very bright. And what was the voltage in the first bulb? Just see, what is the voltage? It was 350 volts. The bulb L1 was getting 350 volts. And just see what is the third bulb, what is it getting? L3, just check, L3, it is getting only 75 volts. The third bulb is only getting 75 volts. Have you seen what is happening now? If you continue to run in this, if you use it in this condition, the bulb S1, L1 will go immediately. Within 5 seconds, the bulb may get fused because it is getting 350 volts. And the bulb L3 is getting only 75 volts. Now this condition is when we are using only a 200 watts load on one phase. My question was, what will happen to the AC? If AC is on, one AC is on and a few lights are on in the other phase. Okay? What will happen to the lights and the other equipment that were on? In case if you put an AC which is 1000 watts minimum, okay, 1 ton AC also is around 1000 watts. If you put that, the voltage in the first bulb will be almost 380 volts. And AC will be getting just 20 volts. And mostly the stabilizer will trip on low voltage because it has got all the stabilizers have low voltage tripping, low voltage and high voltage tripping. Okay? So have you understood now what is happening? What is the importance of neutral in a three-phase lighting circuit? If the neutral goes off, then there will be, because there will be an unbalanced load. When it is balanced, when all the three phases are balanced, then you don't need a neutral. That is how motors, three-phase motors work without a neutral, because all the phases are balanced. Whereas in the lighting circuit, you cannot balance the three phases. You cannot have equal loads in all the three phases because you will switch on whatever is required. Supposing like you switch on a geyser which is 1500 to 2000 watts, then all the equipment in the other two phases which are low wattage will get damaged. Okay? I had actually intended only to take the first question today, but however, after completing the answer, I found there is still time, just very short. So I will just take up 2-3 short questions along with that today. Okay? So I have decided to take question number 3, question number 6 and question number 9. 3, 6 and 9. So first with question number 3. What are the various types of AC and DC motors that you have studied? Okay, that is the part 1 of the question. What are the various types of AC and DC motors that you have studied? I think almost all of you have answered this question, this part. Maybe copied from your notes, I don't know. However, all of you have left out one type of motor, and that is the universal motor. It is a very important motor because it is used in the industries. Okay, in this your hand tools like hand drills, hand grinders, etc. all use this motor, universal motor. Okay, and you will find this motor also in your houses, in your residence. In every residence you will find this motor. It is there in the mixer grinder. Okay, this is basically a DC motor, DC series motor. Okay, it has got an armature with 2 carbon brushes and there are 2 field windings. Okay, 2 poles. two field windings connected in series. If you notice the connection, it will be coming first through to one series winding, then it goes through the carbon brush to the armature, it comes out to the next carbon brush and to the second field winding, and then back to the power supply. Okay, so this is basically a DC motor, DC series motor. So it has got a high starting and running torque. Okay, but it can be used in AC also. That's why it's called a universal motor, and we usually use it for AC only, because the mixers and hand drill, hand grinder, they all work on 230 volts single phase AC supply. So this is one motor that everybody has left out. Okay, but remaining most of the motors have been mentioned. Now the second part of the question is, out of these all these motors, which is the one type of motor, just one type of motor, which is used for 95% of all the industrial applications? This particular second part answer, only one person has answered it correctly. That is that girl who's I mentioned earlier, working in Rajasthan. Okay, she is the only person who answered this correctly, and the correct answer is squirrel cage induction motor. One of you answered it as induction motor, just induction motor. Induction motor, that is not the correct answer, because there are so many types of induction motors. Okay, another person has answered saying that it is the slip ring motor. Now if you are to just go through my questions, 3 of my questions are based on squirrel cage induction motors. Okay, so if you could have just from my questions only realized which is the most commonly used motor, right? And only one question it is based on the DC shunt motor. Okay, only one question. I have not mentioned any other motor anywhere else. Okay, not even the slip ring induction motor in any of my questions. So it cannot be the slip ring induction motor. It is the squirrel cage induction motor. Please keep in mind. So therefore, everything about the squirrel cage induction motor, the starters, controllers, everything which are used with this squirrel cage induction motor, you should learn thoroughly. Okay. So this is all for question number 3. Now shall we move on to question number 6? Now for this, actually, as I told you, I was not prepared today for taking any other question other than question number 1. But since I decided just now to add the other questions, I have made a small sketch, a hand sketch, okay, of a star delta starter. But it is not a complete star delta starter drawing. It's only the power circuit, and that too, it is only about the delta connection when the motor is running in delta. I have shown the main contactor, okay. I have shown the delta contactor. I have shown the overload relay and the connection going to the motor, okay. Now if you look at the drawing, the incoming wire is 3 RYB phase going to the incoming of the starter. If you notice the drawing, it is going directly to the main winding, okay, the main contactor it is going, and from the main contactor it is also connected to the delta contactor, all the 3 phases. 3 phase first going to the main contactor, and then from the main contactor you will see a parallel supply from R, Y and B. It is also going to the delta contactor, which is marked as D. The main contactor is marked as M. And I have shown only the power contacts. 3 power contacts. I have not shown the control contacts because that is for the control circuit. That will be taken up clearly and in detail when I teach you star delta starters. Okay. This is for you only to answer the question number 6. Okay. Because I want to show you where the overload relay is connected. The question was, what overload setting would you use on a 415 volts 3-phase squirrel cage induction motor having a star delta starter and drawing a full load line current of 22 amps. This was the first part of the question. Okay. What overload setting would you use on a 415 volts 3-phase squirrel cage induction motor having a star delta starter and drawing a full load line current of 22 amps. That's why I have shown the motor contactors, main contactor and delta contactor. I have shown the overload relay. Overload relay only the power contacts, that is the thermal elements through which the current flows, not the control. Control is the contacts of the overload relay, which will cause the motor to trip in case of fault overload. I have not shown those contacts because this is only the power circuit, just to show you where the overload relay is placed. Okay, and then the 6 wires or connections going to the motor. On the starter, if you are using a ready-made starter, you will find a terminal block with the 3 incoming contacts. Okay, 3 incoming and 6 outgoing. There are 6 wires going to the motor. That you will find if it is a ready-made star delta starter, you will find the markings there. U1, V1, W1, W2, U2, V2. But if it is a wired starter inside a panel, you may not find those markings. Okay, that is when you will have to understand the drawing completely so that you will be able to give the proper connections to the motor. In case these markings are not there in the starter, and if the markings are there only in the motor terminals, now which is the wire that you have to connect to which terminal, you need to know. So if you understand the drawing, right now you don't have to understand the drawing because this is only to show you about the overload relay, which is part of that question. Okay, but still I have just shown the terminal connector of the motor. There are 6 terminal connectors. Connector I have shown separately on the right side, bottom right side, motor terminal, 6 terminals, how they are placed. Okay, on top the connectors are U1, V1, W1, and the bottom it is W2, U2, V2. I hope you know why the connector is placed like this. Why not U1 on top and U2 down? V1 on top and V2 down. Why it is not like that? Why it is U1, V1, W1 and the bottom connectors is W2 first, then U2 and V2. Why it is? I hope you have understood it. If not, I will explain to you when I take the starters. And the motor which I have just shown as squirrel cage SCIM I wrote, squirrel cage induction motor, 6 wires going to that. Okay, to which terminal which wire is going I have not shown, but if there is a marking on the starter, then you know you can connect U1 to U1, V1 to V1, etc, etc. Okay, now the overload relay, just see, overload relay is placed just after the main contactor. Okay, main supply wires RYB coming to the main contactor, and when the main contactor is on, it goes on to the overload relay, and through the overload relay thermal elements, this is which gets heated up when the current flows to the overload relay. When it heats up, it's basically a thermal overload relay, but nowadays they say that it is a thermal magnetic overload relay. All the starter manufacturers are claiming it to be thermal magnetic overload relay, in the sense that it will also trip on short circuit. But we have observed from practice that when there is a short circuit, actually the overload relay, most of the times it doesn't trip, but it gets burnt. Okay, so we don't believe. We need to have a separate protection for short circuit, again which I will explain to you when I take the starters. Right now that's not required. Okay, this is only pertaining to this question number 6. So now it passes through the overload relay, and then those 3 wires are going to the motor. But if you observe on the right side, again RYB is going to the delta contactor. Okay, through the delta contactor it goes to the motor directly. It is not passing through the overload relay. You understood? Only the current through the 3 wires which is passing through the main contactor is passing through the overload relay. Whereas the 3 wires which are going to the delta contactor is not passing. That means whatever current is flowing through those 3 wires are not passing through the overload relay. It is going directly to the motor. Now this is the connection in most of the Indian starters, star delta starters in India. There are some reasons that again I will tell you later when I take starters. So most of the starters, this is how the connection is, which means it is not reading, the overload relay is not reading the line current. It is only reading the phase current. Okay, understand? Now the current, which is, if you take a torque tester to measure the current of the motor, what the motor is drawing, if you measure with the torque tester from the line means RYB, which is coming to the starter, that is the line. Okay, if you put the torque tester, the incoming wires, it will read the line current. But whereas if you put the torque tester in any of the 6 wires which are going to the motor, it will read only the phase current. Okay. Now this actually is the answer to the second part of this question. How will you measure? What is the second part of the question? How will you measure the line current and phase current of this motor? Okay. This is the second part of the question. If in this star delta starter, if you place your tongue tester in the wires, incoming wires R, Y or B, it will read the line current. But if you place the tongue tester on any of the 6 wires which go to the motor, it will read the phase current, okay, not the line current. And how much is the phase current? Divided by line current divided by root 3. Okay, in percentage, you have any idea how much it is? It is approximately 58%. Okay, approximately it is 58% of the line current. That is the phase current. Approximately, slightly more than that. So actually, we can do the setting on 60%. So the overload relay has to be kept at 60% of the line current. Okay, not more than 60%. Slightly above the actual reading of the current, we set it so that it doesn't trip. But again, this is a very complicated procedure for setting overload relay. It's very difficult to set it at the correct rate. From trial and error, you have to maybe slightly increase or decrease. Because unless you have a very steady voltage and unless you have a steady load, you cannot have a steady current. But in India, you know, the voltage varies so much, and sometimes your machine may not be doing one particular operation only. It may be doing different operations whereby the load will keep on changing. So it is very difficult to get a steady current for setting our overload relay. Secondly, one more thing to observe is that supposing the rated current of the motor is 22.5 amps, okay, and it is reading 22, actually taking only 22 amps. So where will you keep the setting? Setting has to be kept for the actual current that is taken by the motor. If it is 22 amps, you have to keep a little bit more than that. That is say 22.2, like that. Okay. But you should never set it above the rated current of the motor. Supposing instead of 22.5, that is the rated current of the motor, what is written on the nameplate. If the motor is drawing 23 amps, then you cannot keep the setting on 23. Then the motor, if it is drawing like that, the motor in the long run will get burnt. After a few hours of running or after a day or two of running, the motor will get burnt. Continuously it cannot run on overload. Okay, 10% overload it can run for a short duration but not continuously. In case the motor is drawing more than the rated current due to whatever reason, maybe because of low voltage, you know, even if the voltage is low, it will draw more current. Okay, the motor draws more current on full load. So with whatever reason, if it is drawing more current than the rated current which is on the nameplate, if it is for a short duration, I told you earlier, it's okay. But if continuously drawing more than that, then you will have to do something either to reduce the load on the machine, or else ultimately you will have to go for a higher rating motor. Say supposing it's a 15 HP motor, like in this case, this 22 amps motor is actually, if you look on the chart, it is 15 HP motor. That one person has answered this part of the question also correctly, saying it is a 15 HP motor. Okay, it was not a compulsory part of the question. I just wanted you to guess what is the HP of this motor, which I have not mentioned. I have only mentioned the line current. 15 HP motor usually takes around 22 to 22.5 amps. Okay, for 15 volts motor. I have given you the voltage also. Motors are manufactured in different voltages. Some manufacturer manufactures in 400 volts, some in 415 volts, some even 440 volts, but that is very rare. Okay, mostly you will find motors of 415 volts. If it is 400 volts, then the current rating will be slightly higher. Also, for different applications also, the current rating will be slightly higher for the same HP. Like for compressor motors or pump motors, for the same HP, you will find the winding is little different. Okay, because to take several start stops etc. and to start on load, compressor motors etc., you will find that the rated current will be slightly higher than the normal motors. Okay, they are specially wound motors to take care of lots of start and stops and for getting higher torque at the time of starting. Okay, so all those things are I am not able to cover up now. So now since the overload relay is usually placed after that means it is placed on the phase. It reads only the phase current. The overload setting has to be done on the phase current. Lots of people don't know this. Okay, they place it. They even select a overload relay based on the line current when the overload relay is placed on the phase current. Okay, and then the motor gets burnt. So I have had a lot of practical experience, even in big companies, having a lot of engineers there, where all the overload relays were of the line current rating, but it was actually placed on the phase current. But you may find in some, especially some foreign starters, you may find that the overload relay is placed on the line. Okay. Now on the line means if the overload relay is placed above the main contactor, and if the current going to the main contactor and to the delta contactor, both if they pass through the overload relay, then it is placed on the line. Okay. In that case, you have to set it on the line current. But usually you don't see it in the Indian starters, as I told you. But still, to make sure, you will have to check your starter wiring and see whether the overload relay is placed on the line or on the phase current. Okay. So that's it. That is question number 6. Finished? Now we'll go to the last question for today, and that is question number 9. This question also, only one person answered it correctly. The same person from Rajasthan. Okay. She is the only person who answered this question also correctly. If a 3-phase induction motor, while running on load, suddenly slows down and also produces a continuous humming sound, what could be the fault? Okay. If a 3-phase induction motor, while running on load, suddenly slows down and also produces a continuous humming sound, what could be the fault? Okay. If a bearing which is damaged does not produce a humming sound, it produces a different sound, a rubbing sound, which is entirely different. Okay. Secondly, somebody answered that it is because of overload. Yeah, if overload also, the motor may slow down. Okay. Motor may slow down, but it will not produce a humming sound. It's only when the bearing gets damaged that it produces some sort of sound. Okay, or if there is some unbalance, if the shaft is bent and all that, then there will be some sound, but that sound is entirely metallic sound, not a continuous humming sound. Now this humming sound, the fault is what is called single phasing. Single phasing means there are only 2 phases available to the motor. One phase is open. Anything can be open. Sometimes it overload relay, one element may be burnt and open. Current is passing only through 2 phases. Or it may be anywhere on the contactor. One contact is burnt. Or some wire is loose. Any one wire, anywhere. Whereby current is flowing only to 2 phases. That particular condition is called single phasing. Then, how do you check it? The second part of the question was, how will you check to verify whether it is this fault only? All you do is check the current in all the 3 phases. Okay. If you check the current, preferably check it on the line only, line current only. Check it and you will find that 2 phases will be drawing high current and third phase will be drawing either very small current or zero current. If it is fully open, it will be drawing zero current, okay, on that phase. But if it is slightly touching, carbonized and all, if it is loose connection, or if the contact is not fully burned, still there is some carbon and some current is flowing, now very small current it will show. Other 2 phases will draw more current. But the overload relay may not trip because current is flowing only through 2 phases. Okay. So the third element which is burnt, that is not heating up. So it does not correctly trip. Unless there is a severe short circuit and the motor cannot run at all. Okay. If the motor starts stalling, in that case the overload relay may trip. But before that, motor may get burnt. What we have seen from practice, most of the times the motor gets burnt in single phasing. And this is the most common fault. 80% of all motors, they burn because of this fault. Okay. Not because of overload and not because of anything else. Bearing damage and all that. Because all those sounds and noises and all, the operator will be able to make out. But this humming sound, it's difficult unless somebody is experienced. he will not be able to, because machine makes lot of other sounds, and the person with the experience only you will be able to. I will when I get an opportunity, I will show you the single phasing. Okay, when I get a next opportunity to go to the workshop, I will run a 3-phase motor without load. Okay, because with load I don't want to take a risk of running on single phase. The motor may get burnt, motor may stall and do something, or some fuse may get blown. I don't want to do that, but I will show you on a motor without load. Okay, so you can still see the current difference, normal current how much it is, and on single phasing what is happening, and you can listen to the sound. Even on no load, it will create that humming sound. Okay, so it doesn't get noticed sometimes, especially if you use a higher rating motor and if the load is less on the machine. I had a case where almost 3 to 4 months a motor was running continuously on single phasing, because it was running on less than 50% load. So even though in single phasing the current went high in the other 2 phases, the current drawn was still lesser than the full rated current of the motor. So the overload relay was not tripping and nothing burnt also. The winding didn't burn. It was only noticed when we saw that just in the normal checking, when we were doing the current check, even the sound was not very loud, because that machine was making other sound. It was a automatic drill machine, so it was making a lot of sound. So even this humming sound could not be noticed. But when we checked the current, we realized that the contactor only two phases are showing current. Third phase was showing zero current. Then when we checked up, we found that contactor one portion was severe, full carbon was there. It was burnt, and when we opened and checked, we found that one contact was completely burnt. Okay, so this is the question. And if you continue running this motor, I have already mentioned to you, if you continue running motor on single phasing, most of the times if it is running on full load, it will get burnt. Okay, it will get burnt very soon. Within minutes it will get burnt, maybe half an hour maximum. If you run on single phasing on full load, the motor will get burnt. If it does not trip, the overload relay doesn't trip, as per what I told earlier, because we cannot set the overload relay. It's very difficult. Unless there's a steady current, then it's easy. If we have a very steady current, like some automatic machines doing only one particular function, one particular load, and that too only if your voltage is very steady. If your voltage varies also, the current will vary. Okay, so this is the answer to the 9th question. Okay, that's the end of